Functions versus call return. We've created many accidental problems by misusing call and return instructions to implement functions. I explore these issues and point to some ways that might help in backing out of this corner. Call and return instructions were originally included in CPU architectures to provide code sharing. Call return wasn't meant to support functions. It was meant to make code smaller. Here's a simple example. Imagine that we write some code and write it more than once. For example, we load R0 with some variable, we add 1 to it, and then we do it again, exactly the same. Load and add. Instead, we might rewrite the code to load the variable once in a subroutine, and then call the subroutine twice. Functions in mathematical notation mean something else. In mathematics, functions run instantaneously. This isn't true of call-return code on CPUs. A central tenet of computer science is the revelation that one must use the principle of DRY. Don't repeat yourself. Instead of building DRY into our IDEs, we took the lazy way out and misused call to implement DRY. Currently, programmers are responsible for manually rearranging code to be DRY instead of letting the machine do the work for us. Why does it matter? The difference between pure functional notation and call has caused many forms of self-imposed accidental complexity over the decades. For example, the ad hoc muddy thinking about multitasking, semaphores, priorities, etc. For example, the misbelief that destructured data is the same as multiple function parameters. For example, that the dimension of time, t, can be ignored, etc. To make things even worse, call return uses a built-in shared global variable that we call the call stack. This violates the fundamental assumptions of functional notation and requires the invention of epicycles and workarounds. Here's an example of single parameters that masquerade as multiple parameters. We've got a bit of code here that says push 1, push 2, then call the subroutine. What happens on the stack is that 1 gets pushed, 2 gets pushed, and the stack pointer gets incremented. And the top thing on the stack is a 2. When we call the subroutine, we push our return address. That becomes the stack pointer plus 0, or the top of the stack. And the subroutine loads the parameters from the call stack. As I've shown it here, we load SP plus 4 into R0 and SP plus 8 into R1. But in fact, what's there is a single parameter containing 1 and 2, and we destructure it into 2 parts, 1 and 2. And then the subroutine returns. The astute reader will notice that the 2 load instructions simply destructure the input parameter. In other words, the input parameter is only a single parameter, not multiple parameters. This observation is borne out by formalisms such as currying. Several modern languages pay homage to this fact by allowing multiple value assignment and multiple value return. This concept appears in Lisp in the form of destructuring bind and values. Time matters. Parameters arrive and return at different times. Single parameters, though, arrive and return at the same time. As it stands, call is meant for synchronous code only. Concurrency. To build asynchronous code using call, we must invent epicycles such as multitasking. Children as young as 5 years old learn to use hard real-time notation. Music notation, piano lessons, metronomes, all that stuff is hard real-time. Concurrency is simple, but when we want to try to express concurrency in terms of anti-concurrency, synchrony, we need to invent epicycles, which leads to bloatware. We've been using a function-based notation to express programs. Call does not map cleanly onto function-based thinking and to function-based notation. We've gone deeply down rat holes to invent epicycles to work around this notational mismatch. It is difficult, but not impossible, to build asynchronous programs such as internet, robotics, IoT, blockchain, etc., using synchronous notations based on functions. Most programming languages like Python, Rust, C, etc. use functions, and they tend to implement these functions using call and ret instructions. This automatically makes the code synchronous, which quietly uses a shared global variable all of which makes concurrent programming seem more difficult than need be. In general, we need to resort to assembler-level programming using thread libraries to express concurrency. Relational programming languages like Prolog, Minicanred, etc. tend to separate specification from implementation. Such languages actually do not contain functions. The implementation of relations, therefore, is not biased towards the misuse of call instructions. Another way to break free of call bias is the idea of building processes that do not depend on one another. I call this zero dependency, 0D. Maybe I should call this XD for extreme decoupling. I don't know. This technique discourages the use of call as an interprocess mechanism. Distributed computing is the same concept as processes, but on steroids. See the previous section. Note that language features like loop and recursion are essentially meaningless in a distributed context. Note that thread safety is a meaningless concept in a distributed context. Programs on different CPUs are on different CPUs. They are naturally isolated from one another. The concept of thread safety doesn't even need to come up in polite conversation. In 1950, CPUs were very expensive and it made sense to timeshare them. Today, though, we can have candy bowls filled with CPUs. The ground rules have changed since 1950, but we've always done it this way causes us to use 1950s biases when building programs 50 plus years later in 2023. We can put these synchronous concepts back into our expression of distributed computing, but it requires make work and invention of epicycles.